Consider four lines intersecting at points A, B, C, D, E and F. Newton said that if you look at the midpoints of AC, BD and EF, these points are collinear. These collinear points lie on a straight line called the Newton-Gauss line. In this video, we will discuss a beautiful proof due to Roger Johnson in his book Advanced Euclidean Geometry. Now, to discuss this, we need two facts. Fact 1 is a cute fact about parallelograms. Let's denote throughout this video the area of parallelogram ABCD by its diagonal. So whenever I write square BD, I mean area of a parallelogram with diagonal BD. Diagonal of a parallelogram divides the parallelogram into two triangles of equal area. So let's call the equal areas X, X, Y, Y, and the remaining two parallelogram areas as Z and W. So we will have X plus Y plus Z is equal to X plus Y plus W, forcing Z equal to W. So let's remember this. If E is on BD, then AE parallelogram is equal to EC parallelogram. Remember, AE parallelogram means that parallelogram with diagonal AE is equal to the area of parallelogram with diagonal EC. In fact, the converse is also true, and I urge you to try to prove the converse. Throughout the video, we will use the fact and its converse. Alright, let's call it fact 1. The other fact we need is the converse of the midpoint theorem, which is pretty popular. So let's see in what avatar we will need it. So if you have 3 points A, B, C which are collinear and P is any point on the plane, then the midpoints of PA, PB and PC are also collinear. This is simply a restatement of the converse of midpoint theorem. Alright, we'll call this fact 2. Now we are ready for a proof of Newton-Gauss theorem due to Roger Johnson. Okay. Alright, so what is his proof? He says, let's start with 4 lines which intersect at A, B, C, D, E, F as we started in the Newton-Gauss setup. Now what you do is you create a grid of parallel lines by drawing lines parallel to AF and AE passing through D, E, C, B and F, as you can see. Now let's label all the intersecting points. Now we have lots of parallelogram in this setup. First, we note that if you look at parallelogram ABVE, you will see that since C lies on the diagonal BE, from fact 1, we have area of parallelogram AC equal to area of parallelogram CV. Next, we apply this theorem to the parallelogram AFQ, and we note that again we have AC parallelogram is equal to CQ parallelogram. Now we already know AC is equal to CV parallelogram. We also know AC is equal to CQ. So if you put both of them together, we see that CV must equal CQ. But notice that CU parallelogram is common. The green area is common. So if you subtract it, right, we will see that PU parallelogram and US parallelogram are essentially equal. But by the converse of fact 1, this means CUR are collinear. If CUR are collinear and A is any point on the plane, then by fact 2, the midpoints of AC, AU and AR are also collinear. Wait a minute, what are these midpoints of AC, AU and AR? The midpoint of AU is essentially the midpoint of BD because the diagonals bisect each other in the parallelogram ABUD. Similarly, the midpoint of AR is equal to the midpoint of EF because diagonals bisect each other in parallelogram AFRE. So we have midpoints of AC, BD and FE are collinear, which is what we wanted to prove. So we are done.